Today we're going to discover why Wagners Composite Fibre Technologies use Vinylester instead of polyester resin, why we pull wind, where the numbers in the design guide come from, and how those numbers tie into quality assurance testing to ensure compliance. Plus, we're going to find out how fibre reinforced polymer is classed by modulus. Good morning and welcome to our webinar on It's What's Inside That Counts. I'm Kelly Stewart, Marketing Manager at Wagners CFT, and I'm here with Wagners CFT Global Business Development Manager Michael Kemp and Senior Composites Engineering Consultant Rik Heslehurst. Michael is an ambitious CEO and business unit leader with more than 20 years' experience at Wagners, where he has spearheaded significant growth and innovation. Currently, he oversees Australian operations for Wagners Earth Friendly Concrete and is focused on expanding EFC into international markets. Michael is also responsible for the global growth of Wagners Composite Fibre Technologies and the technical development of new products. With a Bachelor of Civil Engineering from the University of Adelaide, Michael combines his tertiary qualifications with deep expertise in business processes, strategic development and product innovation. Meanwhile, Rik is a former aeronautical engineering officer with more than 16 years' service with the Royal Australian Air Force, and that's following 20 years as an academic with the Royal Australian Air Force. Academic with the University of New South Wales at the Australian Defence Force Academy. Rik has been actively involved with several companies as an aerospace engineer advisor and presents training courses for industry in aircraft design, airframe design and analysis, structural joining methods, damage analysis and repair design, and composite structural design. Rik has also consulted for the Australian Defence Force and United States Air Force and Navy, US Army Aviation, NASA, the Gulfstream Aircraft Company, Walt Disney Imagineering, and General Atomics, to name but a few. He's written 5 books, 80 journal papers, and 105 conference papers on composites and bolted structures. He has a Bachelor of Aeronautical Engineering, a Master's of Engineering in Aero, and a PhD, with both postgraduate degrees in research of composite stress analysis and damage assessment. So welcome, Michael and Rik.
Hello.
Before we get started, just a few webinar protocols. We are recording today's event and we'll make the recording public via the Wagners CFT YouTube channel. You can ask a question anytime during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over until the end of the webinar for the Q&A session. And for anyone having difficulty accessing the chat facility, feel free to text your questions directly through to my mobile phone number. I've just put that number in the chat facility there now. Righto, well, let's jump in. Over to you, Michael.
Thanks very much, Kelly. I've just turned my microphone on. I'm going to share my screen and just give us a thumbs up, Kel, once you see that. All good, thank you. And good morning, everyone in Australia. I'm over in Texas, so it's a good evening from our Texas facility tonight for me. Today we're going to run through, Kelly introduced the topic, but we're going to run through, I guess, what's inside our pultrusion. Generally, when we're communicating about our composite materials to people, we're talking about our bridge girders or our boardwalk structures or our poles. And we're very much focusing on the performance of the product. Today we're going to try to talk a bit more about what leads to that performance, and I guess highlight the volume of effort we've gone to develop these products for Australian conditions in Australia. So just as a quick overview, and just because we are focusing today on our Australian manufacturing hub. This is our Toowoomba facility. So you can see our offices and our factories out the back. We've got about 190 people in the composites business, and in Australia we've got 6 pultrusion lines manufacturing about 700 kilometres of product annually. We are exporting from Australia around the world, so you can see we've reached a lot of places around the world now, and that is growing regularly, daily. and of course getting more and more into the places where we already are. So I'm over here in the States in our Texas facility, and from our Texas facility we have done projects in California, New York, Florida, and up into Canada. So far-reaching from here as well. And typically, and I said we're not going to talk about the products, but to talk about where our products go is important when we're looking at what materials we're going to use to manufacture our fiberglass profiles. We have to really have these end uses in mind. So boardwalks, pedestrian bridges, road bridges. So it's a lot of water sort of areas, salt water, fresh water. We're seeing high temperatures, we're seeing low temperatures, and then general exposure to environmental elements. So our key process that we use at Wagners is pultrusion. It's been around for a long time, since probably the end of World War II, and then significant development since. It's the most automated way to combine glass fibre and resin to make a product that we have. So other methods might include filament winding, might include moulding, or even hand layup. But pultrusion, certainly from a labour hours per kilogram or tonne of composites produced, would be the most efficient form. We start with glass fibre rovings at the back of the machine on the left-hand side of the picture. We inject a resin into those glass fibre rovings. The combined, saturated product then passes through a dye. Inside that dye, that resin will cure because of the heaters that we strap to the outside of the dye. So it's a heat-initiated curing process. And then finished product comes out of the dye. And we literally pull the finished product through the dye. So the whole process moves because we are pulling on the finished product. Hence we call it pultrusion. As opposed to extrusion, where we might melt aluminium and push it through a die. Here we are literally pulling the product through the die. So the pultrusion process is literally because we're pulling it. And then we're cutting the sections off as they come off the machine. We're cutting them to length. So it does mean that we can produce very long lengths, and generally we're only limited from a length point of view, we're limited to what we can put on a truck or transport. So just a few photos of that process. The top left photo, raw materials, so it's our glass fibre. So this is not manufactured in Australia, but is manufactured around the world. So in Texas, there is a manufacturing plant throughout Europe, throughout China, throughout India. So there are many glass manufacturing plants around the world, and it is pretty much a commodity nowadays. But glass isn't glass, many different types, and there's lots of tricks to getting it to work in conjunction with a resin system. So it's very important that the two are compatible. The bottom left photo is one of our pultrusion machines. So you can't see a lot on here, I understand, but inside that sort of triangular shroud is a cut-off saw that cuts the product to length. So this is the back end of the machine. You can see here one of our square hollow sections coming off the machine. Behind the guarding, we have a series of hydraulic rams, which are the pullers. They pull in a hand-to-hand pulling method. So when one ram finishes, the other ram takes on, and so on. I like this photo on the top right. You can see that we're setting up to pull, I believe that'll be our 9-inch profile, I'll say, since we're in America, or 230mm circular profile. You can see the glass fibre here is not saturated with resin, so that's been pulled through. We've turned the resin injection on, and we're getting solid product coming out of the die. So it can happen very quickly. It can go from glass, just simply glass coming out of the die, to glass with cured resin, and then of course the finished product that hopefully a lot of you have seen and used. So the pultrusion process does have limitations, and one of the key limitations is that it makes a constant cross-section product. So it doesn't do tapered profiles, it doesn't do special sections, but it does lots of a constant cross-section rapidly for probably the least amount of labour cost, which, you know, for an Australian manufacturing business is very important, per kilogram of product produced. So it is the most efficient manufacturing method, but you can't do, for example, a taper. So with our power pole product, which hopefully a lot of you are starting to see out in the marketplace now, it is constant cross section. So it might be say it's one of our 300 diameter poles. It'll be 300 at the base. It'll be 300 at the top. There's no taper. To the structural engineers that know that you might not need as much material at the top, that is the case. But because of the efficiencies in manufacturing, it's much more economical to produce a constant cross section than a tapered cross section for the same purpose. Now, the products we produce are all contained in our product guide and design guide, which is all available on our website. And we have tables that like the one on the screen, which are full of numbers. I won't test you on the numbers at the end of the presentation, but I think probably the things to take away is that we've modelled them on steel tables. So structural engineers, you know, will easily find the information that they're looking for on these tables. I guess some of the things to look at, the tensile strength at sort of that upwards of 600 MPa. So it's very, very high strength sort of product in general. And I guess a key one is the tensile modulus. So we're sort of down at around that 40 GPa number, compared to steel, where would be equivalent to sort of rebar strengths. If standard steel profiles would be 250 or 350, as opposed to 600. But with the modulus, composites are much less stiff. So if we would say a modulus around the high 30s to 40 mark, whereas steel would be 200. So it differs from steel in some areas, and but similar in others. So we've produced these tables. So today, really, what I want to get into is what's behind these tables and how did we develop them. So the first thing that I'd really like to focus on is the resin selection, and there's three main categories of resin when we're talking about pultrusion. There's one other as opposed to the three on the screen. The three on the screen being epoxy, vinylester, and polyester. They're the real common ones. Polyurethane is getting more and more traction, but from a cost-benefit analysis, probably isn't quite there yet. But we are seeing it come through, so it's something to watch for the future. The differences between polyester and vinylester is really what we're going to focus on. If we're talking about cost of the resins, polyester is the cheapest, vinylester is more expensive, and epoxy is more expensive again. And what you can see is that there are, the trend of the three is that polyester is the lowest performing through to epoxy. Now these are resin properties and resin modulus, not of a combined laminate. So we're just looking at the resin itself. Now for the Wagners products, different applications will be different. But for Wagners products, we're primarily talking about structural products, beams, poles, bridges, these sorts of things. So one thing that is important to us is this strain capacity, or on a resin data sheet, you'll see it called elongation to failure. And what we see is that with a polyester, we get a relatively small elongation to failure. With a vinylester, it's bigger, and with epoxy, it can be bigger again. When we look at a stress strain curve, it's this first little, I guess, glitch on the graph. Now most of Wagners products, this curve won't be quite so much a curve as it will be a straight line on the stress strain curve. But what we're talking about here still applies, which is where we get either our first crack or our first noise. You might not notice a difference in modulus, but you'll start to hear first, we call it micro cracking, or like you'll literally, in a test application, you'll literally hear it. You'll hear it'll start to crack. And with a polyester resin, observationally in my 20-year history at Composites, and of course doing the maths, we'll see that this first cracking will happen at a fairly low number. It might happen at 50% of the ultimate capacity of a sample. With a Vinylester resin, we're seeing that right up at much higher. So typically with our products, we're starting to hear that cracking at upwards of 90% of its final capacity. So what does that mean? If we move this line from a fairly low area on this curve up to a higher area, it means that we're in our operating range of the product, we're not getting that cracking. So we're going to see it last for a longer life. Those initial cracks are entry points for whether it's sitting in water, sitting in acid, or some sort of corrosive area. It's the initiation of a durability issue potentially. So going to Vinylester, what we see is that we get a higher tensile strength, a higher tensile modulus, and we get a better durability outcome. And I'll just play this. I might have to reload my screen quickly, Kelly, because I want you all to, hopefully, I want you to listen. I need to include sound when I share my screen. So we'll try again. Hopefully you'll be able to hear this pole. So we're applying a load to a pole. You can see that's already got a significant bend in it. It's near failure. We are upwards of 90% of its ultimate capacity. I'll press play and I'll let you listen to the cracking noises that we hear. So up until that final failure, we could have released the pole, and we would have almost gone up and down the same load deflection curve. It would have, you would not have noticed a loss of stiffness. So hopefully that worked and you heard the sounds. But that cracking noise is really an easy indication if you're doing a test of what's going on. With a Vinylester resin, you hear it late. With a polyester resin, you're hearing it from maybe 50% of its ultimate capacity. When we talk about water, so a lot of our product is going into saltwater environment. That's why we're using it. We're trying to get away from corrosion of traditional materials. Vinylester resins, which we use exclusively, because initially because of the structural properties I'm talking about. But as we did more and more work, we've realised that it's much more resistant to use in the water and hydrolysis, certainly than polyester resin. So a cheaper resin, and we have to compete with cheaper resins and cheaper products, but generally there's not a lot of understanding about why we've selected the sort of profiles we have. So if we're talking about marine piles or even in the vicinity of marine applications, so either in the water or certainly exposed to the water, we definitely have seen, and there's a lot of data now on the performance of Vinylester over polyester. It does come down to a fair bit of chemistry as well. So we're seeing that because of their superior chemical stability, and also their tolerant of stretching or their elongation to failure, as we were just talking about, we're not getting that micro cracking in the matrix, and we haven't got that avenue for the onset of moisture absorption and therefore durability issues. So if we've got our resin right, and we're starting to process product, it's important to process a good product. And this is an easy thing for you to check, whether it's in your boardroom or in the field. A very simple test we do on product is we use die check. Now, if you don't, this is common in the engineering workshop. It's used for weld testing, for example. But if you don't particularly want to go out and buy some die check, it is at Bunnings and other places. You can use a Sharpie, a texter, or even a whiteboard marker. And if you cut a piece of pultrusion, you sand it so it's fairly smooth as you can get it, and then colour in the end of the pultrusion with your texter, whiteboard marker, or your die check, and then remove any of the excess. And what you'll see is that the die check or the whiteboard marker will penetrate into the pultrusion where there is a crack, or indeed where there is dry fibre. It'll become very obvious. So you probably don't need to guess which side of these is the Wagners one. It is the left. The lines that you can see, the vertical lines there that you can see, are marks from the saw where we've done a saw cut. And the issues that we see in imported product here are these cracks in the profile, and they're fairly regular. When we process Vinylester resins or polyester resins, there is some shrinkage involved, and so compensating for that shrinkage in manufacture is very, very important. If you don't, you will get cracking inside the section. So again, it's an avenue for moisture to get in and to start to cause a problem. It all leads to durability. Now, we haven't spoken about the glass yet. Obviously, this is the important part. The glass is the bit that actually provides the structural strength. A quick story. This is one of our first projects in Australia. It's the Cootes Crossing Bridge. We bought in pultrusion. These are the beams that make up this bridge. So we're talking 2003, 2004. We were bonding imported pultrusion. We were stacking one on top of the other to make webs. Now, the traditional pultrusion, 90% of it is longitudinal fibre. So we would have to hand laminate on the outside of these girders with a plus and minus 45 degree double bias glass fibre, so that we could carry shear loads, which happen at plus and minus 45 degrees. I guess through some innovation sessions at the time and through frustration from having to do so much hand laminating, we said what we really need to do is to get this double bias glass into our pultrusion. Now, that simple comment led to development of pull winding. So we're one of the largest pull winders in the world, and pull wind some of the largest profiles in the world. And you can see today, this is a 250 deep by 100 wide rectangular hollow section. You can see our blue line. I've just marked this up, but to indicate we've got longitudinal fibre, so still lots of longitudinal fibre, and then plus and minus 45 degree fibre for those shear properties. So we've got our resin, we've got our glass, we're making good pultrusion. How do we work out how strong they are? I will accelerate a little bit here. We do have a lot of data on this, but we're using an ASTM standard D7290, which very specifically covers the derivation of characteristic values for use in civil engineering structures. Very simply. There's not a lot of disputing it. That's exactly what it's for. We have to determine material properties in accordance with a standard such as this one to be able to use it in accordance with our loading codes. Australian loading codes are factored loads, and they require material properties that have been downgraded, we'll say, to account for manufacturing variability. We use a Weibull distribution. Well, the standard uses a Weibull distribution as opposed to a normal distribution, and we are calculating a characteristic value. So I'll try to explain that with an example. You can see that if we're talking about a normal distribution on the left, it's the same either side of the mean. A Weibull function enables you to slant your distribution to account for what's really happening. And then our characteristic value at the end of the day is right down here, so it can be well off your average. And these are the numbers that we're putting in our design guides. And it's critical, if you're a specifying engineer, that you understand that the numbers that you're using for design work, and you want to be using a characteristic value. So just to give you a quick example of what that means, here's 10 tests. These are actually a compression test on a sample, ranging from 436, I think, is the lowest, up to 496 might be the highest, I think, across 10 values. When we put that through this process, we get a characteristic value of 395. So you can see it's a considerable downgrade. The average of 459, we're well below the average. We're more than 2.5, is it maybe, standard deviations away from the average. So what we are giving you a characteristic value. It's this 80% confidence line, and these are the numbers that we are producing in our design guides. I might accelerate. I'm probably running a little bit over time, but we're testing everything. We're testing connections. We're testing coupons. We're testing, shear. We're testing fully worked up samples through to full bonded beams. So these are also in our design guide. This is one of our I-beam profiles. And you can't just test one. You actually have to test multiples of them to account for structural variability in manufacturing. And you can see we are generally pretty good. We're operating at typically a 5% coefficient of variation of that order with most of our works. And then we have to do a lot of quality control to make sure that we are hitting those targets. Why it matters, that I-beam goes into a bridge, and then this is a Nolan's truck delivering fruit and veg on the Gatton Clifton Road, and that truck driver will have no idea he's driving across a Vinylester ECR glass pull wound pultruded beam, but he'll get to the other side, and that's, I guess, why civil engineers operate this way. So what does all this come to? So from a specification point of view, what we're pushing now is the designation of a grade E40. Particularly in Europe, we've seen them start to push grading to talk about, we have grades for steel, we have grades for concrete, grades for composites. And it is a marker of durability. It is a marker of strength and stiffness. So in Europe, they have E17 and E23, generally based on modulus, and which comes down to having good pultrusion, having low void contents, these sorts of things. So we have sort of derived E40, and everything, and the summation, as I've got on the screen, of everything that we've presented here today, the glass selection, the resin selection, the processing, and the quality control, leads to being able to designate a grade of E40. And it is all of it. It's not one test. It's not an average of tests. It is the system of developing the product. And that's simply how we make sure. Thank you very much. I'll throw it back to you, Kelly. And yeah.
Wonderful. Thank you very much, Michael. Hugely informative, lots of content there. If anybody has any questions for Michael, feel free to put it into that chat now. We can ask those questions in the Q&A session. But I'm very pleased now to introduce Rik Heslehurst, who's our guest speaker today. Rik, I'm handing over to you.
Thanks, Kelly. Got to find the shares.
Right next to the leave button, Rik. It's a real issue that I have the team. To anyone who's used to presenting, the number of times I've pressed the big red leave button instead of the stop sharing button.
Good morning, and for Michael, good evening. I've been working in the composites industry for pretty close to 45 years, over a range of things, starting with a project on e-glass in my final year at university, in bachelor's engineering degree. The things I want to keep you in mind are these three words. For composite materials, they are heterogeneous, they are orthotropic, or anisotropic in some cases, and they are laminated. And those three words will define your design and also provide you with information when things aren't going right, one of those areas is your problem. Now, for me, as I said, I've been working in the industry for 45 years, and here's a couple of samples of jobs that I've done in composite materials. The composite material doesn't matter what product it's on. The selection of the materials, the fibre and the resin, is important for the product, but all of this, the stress analysis, all of the deformations and such, are basic engineering design work, irrespective of what platform they are on. So as I said, we remember 3 words. First is heterogeneity. The material is made up of multiple materials, fibre and resin. It can be other materials as well. There is an environmental focus. It's the resin that is generally the key issue with the environment: temperature, moisture, fluids, etc. The stress distribution is also based on the fibre matrix modulus share, or the stiffness ratio, the fibre stiffness to the resin stiffness. And the fatigue and damage tolerance, which Michael showed some aspects of damage tolerance. So here we can see fibre ends in a resin system in the first 2 pictures. And you'll note that it's not uniform. There are spaces of more resin. We refer to those as resin-rich areas, particularly in the centre picture. I put a sandwich panel there, and the sandwich panel is made up of 5 materials: the resin and fibre in the facings. The Nomex core has a cloth, an aramid cloth material with a phenolic resin, and there is a adhesive layer between those. So there's 5 materials, each doing their own thing. They're not becoming different materials. And so when you're selecting your individual materials, make sure you understand what they are going to provide you with. You know, the superiority of resins. When you look at resin systems in the whole, here is a whole range of resin systems. Their modulus are typically similar. Their strengths are not too dissimilar. There are ones with lower and some higher, but generally they're close together. Likewise, their density is pretty close to 1.2 as an average. So the resin itself provides more than just a strength issue. It's more there to provide environmental resistance and support of the fibres. In the mechanical performance, strength and stiffness in particular, fibres dominated. If you do not have fibres in that direction, resin tends to dominate the performance. At some stage during this week, grab a piece of cloth material and pull it in the fibre direction, and you'll feel how it's resistant. Grab the opposite corners and pull, and you'll feel that it wants to open up. There is no fibre or resin, no fibres in that, and that's what will be resin-dominated properties. And the fibre-dominated properties can be 50 to 100 times greater than that of the resin system. So here, for example, is a number of different composite materials and some metals, and I put an epoxy in there, and you can see that their densities are of the fibre systems are fairly similar to the epoxy material. And then if you look at their modulus and strength being the bar, modulus being the dot, we see that our fibre systems have a greater value of than the epoxy systems or the resin systems. Then the next thing I said that you need to remember is orthotropy. This means that the properties in the plane, in the XY or 1-2 plane, are variable from 0 to 90 degrees. So looking at the cloth here, the woven cloth, you can see that the properties will be maximized in the direction of the fibres. At 45 degrees of that, there is no support of the fibres. It's all based on the resin system taking that load. So we turn the cloth 45 degrees to take those shear loads, to take those torsional loads. I've included anisotropy, or the 3D effect. If there is no fibres through the thickness, your through the thickness properties are resin dominated, unless you stitch. And through the thickness stitching adds a little bit more to the resin, but the stitching is generally pretty light. So through the thickness loading, resin dominated. Shear performance can be resin dominated if you do not have fibres in the 45-degree direction. Bolt bearing performance is also based on these properties, because bolt bearing can be off axis or distributed off axis and will be resin dominated if you do not put in enough 45-degree plies. Also note that the fibres have different tensile compression strengths. So for example, in typical carbon fibre, the tensile strength and the compression strength are fairly similar. In glass fibre composite materials, the compression strength is about 60% of the tensile strength. In many of the aramids, such as Kevlar, the compression strength is only 30% of the tensile strength. And for interest, boron fibre composite materials, the compression strength is twice the tensile strength. Also understand the term of warp and fill fibre performance. In cloth materials, typically such as 7781 style glass, there are more fibres, about 78 fibres in the longitudinal direction and 73, I think, in the fill direction. So you end up with some variations in the properties, and that might become an important thing to consider. When think of a plate, and you put under this plate a series of springs of different coil diameters, different wire diameters, different wire material. And as you apply a uniform displacement deformation on this, the springs will deform the same amount, but their load share is based on their stiffness. And the stiffness, essentially Young's modulus times the cross-sectional area divided by the length or thickness, gives you that if it's greater, K3 for example is greater, it's going to take a larger proportion of the load. This is important in the strain-based design of composite materials. If we apply an end load to a composite material that's made up of plus minus 45, 0, 90 and symmetric, you'll note that the fibre direction is much stiffer to the matrix direction, the 90-degree material, and that you end up with a greater amount of load in the 0-degree ply. And then when you look at the fracture, it'll be based on the ratio of the fracture load to that of the fibre strength in that direction. And as you saw on that pipe, that cracking that was being shown by Michael is essentially some of the resin cracking here, and you're hearing that, but the fibres are still taking the load. That's why it didn't break suddenly until the fibres fractured. In this case, they fractured in compression, and on the early introduction video, there was a compression failure because the glass fibre compression strength is less than the tensile strength. Now, not wanting to look at all of this, but you can find that for a composite material, you have a range of configurations that you could use for your material, unidirectional, cross-plied, 45 bias, down to things like the stitched quad axial. And the modulus, longitudinal, transverse, in the plane, and in plane shear and strength, there is a range of better performances. And if you look at the in-plane shear performance in strength and modulus, you'll see it's always best when you've got 45-degree plies in there. So important to keep that in consideration with your complex material as a composite material. So let me tell you a story about a tale of the superior bumper bar on V8 supercars. Many years ago, a decade and a half, I was doing a presentation on damage tolerance of composite materials, and there were two members of the Ford Performance Vehicles team who manufacture the bumper bars for the Ford Performance racing cars. And they asked me if I could look at improving the damage tolerance of their bumper bar. So I went down to the facility and they showed me the bumper bar and how it was built. And the configuration out of an 800 satin carbon fiber weave was 0, 0, 45, 45, 0, 0. So the zeros are all across the front, 90 degrees is vertical, and 45 is obviously at 45 degrees to that. Now, I ran the analysis for them on that material, and this is what is called the stiffness matrix, in-plane stiffness matrix. 48.4 is effectively the Young's modulus in the axial direction. 47.9 is effectively the Young's modulus in the transverse direction. And the in-plane shear modulus is 11.3 based on the 45-degree plies. Now, when you bend the bumper bar, bending it in plane and getting that bending deformation, the effective Young's modulus in the longitudinal direction, bending direction, is 55.1 and about 54.4 in the transverse. But look at that shear torsional resistance, 4.7. So they asked me what I could do. So I said, well, apart from a couple of minor details, change the configuration to put 45s on the outside. Remember, the title of the seminar is What's Inside Matters. So put the 45s on the outside. What does that do? It doesn't change the in-plane matrix. It's just based on the number of plies in the different directions. But the outer plane or bending stiffness matrix, flexible stiffness matrix, you can see that our axial, longitudinal, and transverse have reduced by about 15 megapascals, and so about 15%. But the torsional value has gone up almost 5 times by just changing the position of those plies. So what does that mean? Well, in V8 supercars, a lot of love taps occur during the race, and typically to bumper bars. And a bumper bar could be dislodged, but not necessarily come off. And you would be technically black flagged to come in and replace the bumper bar. The front bumper bar plays an enormous role in the cornering speed. And also, as you're going around a corner, if someone bumps you, you are pushed off your racing line and you have to back off. So I didn't know what happened after I did this in the November of one year. And during the racing season, my son, Cameron, who is a motor mechanic for Toyota, was watching the race, and he said, "Oh, Dad, come and have a look at this." And I said, what's going on? He said, the stewards have gone to Ford Performance Vehicle to inspect their bumper bars because on average, they go through 5 to 7 bumper bars during a race meeting. Over the last couple of races, Ford Performance Vehicles were only going through 2 or 3. And the rest of the racing teams thought they were doing something illegal. Well, they weren't. I mean, we just changed the ply position. We didn't change costs. We didn't change labour. It was the same bumper bar with just ply position changes. So what was the outcome? Well, basically, I should say it's all based on energy. So a vehicle going at a certain speed pushes into a bumper bar. If you get more deflection in bending, you have less force. And so it stops you pushing you off the racing line and causing damage to your bumper bar. So Mark Winterbottom won the Drivers' Championship that year because he stayed in the top 10 positions longer than others because of his bumper bar and his racing conditions. And the last part to remember is laminated structures. Stacking sequence, as I've talked about, bending and torsion, and you can tailor to meet those requirements quite easily. Ply distribution orientations are important to understand, and they give you your modulus of the structure. Resin-rich zones between plies, manufacturing processes create areas where delaminations and free stresses and delaminations can occur. So be understanding that, and as Michael did show you, those cracks in the profile of an imported beam, they are going to make life difficult for you in the long run. Now, this is a de Havilland DH98 mosquito fighter bomber called the Wooden Wonder. It was made of plywood and balsa core. And in particular in the fuselage, when the rudder is depressed, the center of force sits up high, which is going to cause a rotation of the tail cone or the fuselage. And to stop that rotation, which is torque, the plywood was placed at 57 degrees based on the low cases, but 57 degrees to overcome torsional deformation of the empennage. It works. It's been working for a long time. Just to finish off, just a couple of highlights on things that I've done that had been I felt quite chuffed about. Was this is a Skycraft Australian company building a satellite, and the structure that these satellites on is called the satellite bus. And the company I was working with had designed this out of carbon fibre, and they were having some issues, and I received it and asked to have a look at it, and all I did was change ply positions, and they achieved their design requirements, which was quite exciting. This is a Aero Environment Puma UAV. It's got a 3-meter wingspan. The company that was building this for us in for the Australian Army, putting solar panels on this, they didn't do too great a job, and so I redesigned the wing so it would take the low cases. But the overall result was we went from 4.5 hours midsummer endurance to 9 hours. And then the last one here is this composite leg here from Scott Reardon, who came second in the Brazilian Paralympics, and then spoke with me about how he can improve his time. So we did a little bit of work on changing the stiffness of his racing leg, and I was able to say that he could get at least half a second improvement. Well, he lost the race in Brazil by 1/4 of a second or less, and then he won the following 4 years in China with that half a second. So it was pretty amazing. So finishing up, remember the materials are not just a single solid material. They are made up of different materials. Their orientations are important to achieve the properties of your structure. They are a layered material. Be careful of working with finite element analysis with orthotropic solid modelling. You may not be modelling it properly. I've got a couple of stories that relate to that. Be careful of vendor properties. Make sure that the vendor properties that you receive is what you can achieve. It's all based on manufacturing, called fibre volume fraction. If you're not sure, always ask. Do not guess. Remember, the work that we as engineers do put people's lives at risk. So here is a smart composite shell leaving the scene of the accident. Over to you, Kelly.
Fantastic. Thank you so much. We've gone a little bit over time today, but why wouldn't you when we've got two such fantastic guest speakers that are so engaging? So we are very shortly going to dive into the Q&A session. I see that we've got some great questions there. Just before we do, and to give the guys a chance to have a look at those questions that are coming in, I'm just going to quickly share my screen with you. I wanted to tell you about Wagner's new design guide. So the design guide version 2 has just recently been redone by the team here. The design guide is intended for structural design engineers who wish to design structures using Wagner's CFT pultruded FRP. and it provides engineers using this publication with all the information required to design structures using Wagners CFT products, including design methods and design capabilities. So you can use the QR code on the screen there now to get your free online copy, or I've just popped the URL link in the chat there as well. And I'll make sure that when I send out the follow-up email today, I'll include a link to that new design guide that's got all the updated information in it as well. And I just wanted to let you know, if you don't already receive the Wagners CFT monthly online newsletter, register now to get your free copy using the QR code on the screen or the URL that I've just popped into the chat facility. It comes out monthly. It's full of great content about designing, constructing and working with FRP, and the October edition is no exception. We're going to be looking at the next webinar, which will be featuring Michael Downing from Whitsundays Regional Council, and he's going to be talking about the total cost of ownership. So that's going to be a great one for councils. There's also a very inspiring story about a construction industry body that's sparking the imagination of women to pursue professional careers in construction in a very unique way. So look out for that one. And there's going to be a case study on the manufacturing, design and installation of light poles as well. So if you don't already receive that newsletter, use the QR code or the link in the chat there now. So I'm going to stop sharing and we're going to jump into some of these great questions. Michael, have you had a chance to have a look at those?
Oh, I have, Kelly. So happy to
we might start up with Andrew Kirk's question, if that's all right with you.
Sure. Andrew's question, for those of you that haven't seen it in the chat, is, are there future plans to manufacture 100% non-conduction light poles? Currently, the access hatches and tenons are conductive. I think, Andrew, the simple answer there is we've got to start somewhere, and using sort of commercially available things to put inside our light poles is where we've started. But absolutely, if there's a market demand for it, we're happy to produce them. And the more there are, the more we'll refine it. So at the moment, we have been looking at non-conductive access hatches. So we'd be keen to talk more about that with you, I think. And it's definitely demand driven. So if there's a market for them, we can absolutely do that work. The next question that we've got there, and Kelly, you put one in, it might have come from someone else, but can delamination initiation at composite structure free edges be inhibited? So, and I'll let Rik have a crack at that as well. But in my, everything we do at Wagners certainly is trying to prevent peel in structures or peel in bond lines or peel in the profile, and trying to ensure it's the detailing at connections really that will ensure that we're not causing further delamination in anything. Rik, do you have anything you can add to that?
Sure. Delamination initiation is really based on through the thickness stresses that are developed as a result of the in-plane loads at the edge of a structure. And the way that the laminate is configured in through the thickness layup plays a big role in that. And one of those things is to not try and put too many layers of the same orientation together in a stack. So for unidirectional 4 plies, or for cloth maybe 6 plies. The other is, if you've got a free edge, you can ease the issue of delaminations by just laying a single biaxial layer around the edge as a cap. And most of the load now is taken by the fibres in that cap, not through the thickness part of the resin of the laminate.
Excellent. We've just got a question. James has popped in there as well. How does Wagners Composite Modulus account for the non-linear behaviour of materials under different loading conditions? And how does it compare to other models in terms of predicting long-term performance of composite materials? That might be a good one for you, Michael.
I think so. I guess to bring it back to Wagners products, if we're talking about the behaviour under load. A lot of our, assembled components are linear. We get linear behaviour on a stress strain or load deflection curve, of one of those I-beams, for example. And what we're really doing is managing the internal stresses in the profile and making sure that we're not overloading that individually. So when we're looking at 98%, I'd say, of what Wagners makes, we're governed by stiffness. We're not governed by strength. So for a road bridge, we're talking about a deflection at midspan, or a pedestrian bridge. For a light pole, we're talking about 5% of the bendable length translation at the top. So it's generally these practical deflection criteria that are governing the design of our composite structures. And what that means is we're operating at a very low percentage of our ultimate capacity, which gives us a very good fatigue life. And that's why we get, I think I might share my screen again if it's not too much hassle.
While you're doing that, Michael, I'll add in that the fibre properties are linear elastic to failure. It's the resin properties that provide the non-linear behaviour.
Yeah.
And if you're loading on axis, it's linear elastic to failure, which one of your plots showed. That one.
So yeah, there we go. We're thinking the same thing, Rick. So typically, this beam, if this is our failure point up the top, will be operating. So as the Nolan's fruit truck was driving over it, it's operating at a fairly low percentage of its ultimate capacity, and because of that, we get a large number of cycles to initiate a fatigue issue. So because we're generally operating at that low percentage of its ultimate capacity, we get very good fatigue life.
Great one. I think we've answered that question. I'm going to jump to this question that has come in on text on my mobile. What software do you recommend for FRP laminate design? And I think we might make this our last question too. What software do you recommend for FRP laminate design?
How much are you willing to pay?
Let's give them the two extremes, maybe endless budget and we're on a budget.
There are some free software that are reasonable that you can download, but if you're wanting to go to the high end, Hyper Composites is probably one of the better ones.
Okay, great. Well, I think there's no more questions coming in there, and I think we've answered the questions that are in there. So I'm going to conclude our presentation today. Just before you go, I'm going to quickly share my screen. If you'd like to share your thoughts on today's webinar, please feel free to complete the feedback form by using the QR code on the screen or the URL that I've just placed into the chat facility. Perhaps you'd like to be a guest speaker too. If that's the case, there is a section on that form if you'd like to fill that out, or reach out to me on LinkedIn, send me an email, give me a call. I'd love to hear from you. I also just wanted to let you know about our next webinar, which is on the 30th of October, and that's going to be featuring guest speaker Michael Downing from Whitsunday Regional Council. He's the Manager of Capital Programs, and we're going to be talking about the total cost of ownership of community assets and the benefit to your bottom line with FRP structures. Whitsundays now has quite a number of FRP structures on their asset register, including Bicentennial Boardwalk. So that's going to be a good one to tune into and find out from the people on the ground the impact that structures are having on maintenance budgets and capital expenditure. Again, you guys know the drill. You can use the QR code on the screen, or I've just popped the URL into the chat if you'd like to register for that webinar today. That concludes our webinar on It's What's on the Inside That Counts. We hope you've enjoyed yourself and got a lot of information out of today, and we look forward to seeing you in October. Michael and Rik, thank you so much. Huge amount of information to digest there, and we've really thoroughly enjoyed having you both here today. So we're going to No worries. We're going to exit on the introductory video that we came in on, and we look forward to seeing everybody in October.